Okay, the next section I want to look at is the reactivity of amines. And we've actually seen some of these already, so I wanted to start off with a little bit of review. We'll start off with acylation. And we actually covered acylation briefly when we talked about amide preparation in our carboxylic acid chapter. And the way we do this is you can take an amine and you can react it with one of two different reagents in order to make the corresponding amide. So in this case, if we started out with aniline, we could make the corresponding amide that would look like this. And it's called acylation because this group that we've added on is an acyl group. You may see this in your biochemistry courses. Oftentimes it's just abbreviated as AC. So the question is, how do we get that on the nitrogen? Well, you have one of two different ways. You can react this with an acid halide, or you can react it with an anhydride. Either one will work well. Obviously, the acid halide is going to be a lot more reactive. The anhydride is going to be a little bit more selective, meaning if you have other nucleophiles present, the nitrogen is going to react with the anhydride more readily than something like an oxygen will. So a good example of this in practice is with the creation of Tylenol. So if we think about Tylenol, we do an acylation reaction where we want to specifically acylate that amine, not the alcohol. And the amine is more nucleophilic, so we don't want to use a really, really strong electrophile like the acid halide. So instead, we can use acetic anhydride in a stoichiometric amount, and we can preferentially acylate the nitrogen over the oxygen. And we can make Tylenol this way. All right, just a small PSA about Tylenol. Tylenol is an interesting drug. We oftentimes take Tylenol for common aches and pains. However, its effective dose versus overdose is quite narrow. So in particular, if you have kids, you should never ever give kids adult Tylenol because you might accidentally destroy their liver. It's a really nasty drug to accidentally overdose on, so we really need to be careful with how much Tylenol we take and avoid giving children adult doses of Tylenol, even if you don't have the children's Tylenol at home. All right, so let's take a look at some cool tricks that we can do with this. Okay, so acylation can be used as kind of a workaround from some of the common problems that we would run into. So let's say we've got aniline, and our goal with aniline is to brominate it. So specifically, how do we get a bromine on the para position? Well, if you just do the thing that most of us would try and try to do Br2 and iron tribromide, you're going to run into a problem. Instead of getting this, what you're really going to end up with mostly is your over-brominated product. And the reason this happens is that amino group is such a good electron donor, this reaction is essentially going to run away from you, and you're going to get over-bromination. All right, so then the question is, well, how can we avoid this? Well, one workaround is to acylate that nitrogen, and by doing that, you're going to actually convert it from a strong activator to a moderate activator, right? Because if we think about this group right here, this is far less electron donating because now we've got competing resonance where we can pull this lone pair out, not just into the ring. So this is going to be a moderate activator. In addition, this provides some nice steric bulk too, right? So this region and this region is kind of blocked, where over here in our starting material, it was a lot more accessible. So we are going to prevent those ortho positions from reacting as readily. So now we can go ahead and do our bromination with elemental bromine and iron tribromide, and we can get that bromine to install primarily in that para position, but that acyl group is going to stay put. So now we've got the bromine right there, and to remove our acyl group, all we need to do in order to pluck this off is to treat this with acid and heat, and we can hydrolyze off that amide. So we can go ahead and just write H3O plus and heat, and we can get back to our desired product without running into the overbromination problem that we saw above. So like I said, acylation is a good trick for adding some steric bulk, protects your ortho positions from reacting, and it can tamper down the strong activating effects of a nitrogen. All right, one other thing that I saw, or that I wanted to show you, is also related to aromatic substitution chemistry. And this is one I really didn't get into during the chapter just because there were so many reactions we had to cover anyways, but it's a pitfall. And that is, if we have aniline and we tried to do a Friedel-Crafts reaction with something like methyl chloride and aluminum trichloride, you're going to get either no product or a mess of products. And so then the question is, well, why didn't you show us this in the chapter? Well, the reality is a little complicated. So if you think about this aluminum trichloride, right? This aluminum is a really good Lewis acid. It's got this empty p orbital here. And ideally, what we want to happen is this chlorine to attack in, right? However, there's a competing lone pair that can add in. Specifically, this lone pair on the nitrogen can add in. And when that happens, you're essentially going to coordinate all of that nitrogen with this Lewis acid adduct and kill that catalyst altogether. So let's make a note here that the Lewis acid catalyst coordinates with nitrogen. And this is because nitrogen is such a good nucleophile. Okay, so let's take a look at the solution for this. Well, the solution is kind of similar to what we saw above. And that is, if we have aniline, let's just acylate it first. So we can first react this with our acid halide. We can turn it into an amide. It's still an activator, but it's a moderate activator. But now the lone pair on the nitrogen really isn't going to coordinate with the aluminum because it's delocalized so much, it's not going to be as available. So now we can go ahead and we can say, all right, let's do our Friedel-Crafts reaction. We're going to get para substitution. Let me clean this up a little. We'll get our methyl group to install on the para position, again avoiding that problem of ortho substitution. And then to get rid of that acyl group, just like in the top example, we'll treat this with acid and heat. And we can get our final product, also known as toluidine. It's kind of this hybrid between our aniline and our toluene. All right. Oftentimes in the book too, instead of showing this as NH2 as the final product, it'll show it as NH3+. If you want, you can show it that way. I'm not going to be super picky. I just want to make sure that you clearly understand that you can cleave that amide by using acid and heat. All right, there's another reaction I did want to cover that's really interesting, and this is called Hofmann Elimination, and it might sound familiar. We talked a lot about Hofmann elimination when we covered E2 chemistry, right? And if you remember when we did E2 chemistry, the Hofmann product was the product that gave you the less substituted alkene. And the way we always did this in first term organic chemistry was by using a big bulky base. In this case, we're going to actually tweak it a little bit. So I want to show you how this is done. And the mechanism is pretty straightforward. If you have an amine, what we're going to do first is we're going to purposely over-alkylate it. Let me clean this up. So we normally just use a cheap alkyl halide like methyl iodide in excess, and we purposely overshoot. And when we do this, we're going to get this quaternary ammonium salt. Normally it's something we want to avoid, but in this case it's kind of helpful. So what we can do in this case is then treat this with a base. So you can treat this with NaOH. The sodium, again, is just a spectator. Our hydroxide is going to act as the base itself. And because this has a positive charge on it, it's going to be a pretty good leaving group, right? Because when it falls off, it's going to be neutral. So just like with E2 chemistry, we have to go after beta protons. So in this case, the alpha position's right here. That's the position with the leaving group. Beta positions are one away. And it doesn't really matter which beta protons we select because they're all equivalent protons. So I'm just going to go ahead and draw beta protons over here. And we can do our E2 reaction like this, clamp down, and kick off our leaving group. And when we do that, we can make our alkene. And then our leaving group, like I said, is going to be neutral. Let me clean this up, sorry. So NMe3, our trimethylamine, is going to be our leaving group. All right, so this is the whole idea behind the Hofmann elimination, at least with amines, is you can purposely over-alkylate an amine using an alkyl halide and then treat it with a base like sodium hydroxide. But there's actually a variant on this too, and that is if you treat this with silver oxide, specifically silver 1 oxide, something interesting happens. What happens is the countercation in the first reaction, which is I-, let me go ahead and draw that up here. Whoops. This counteranion, oh my goodness, won't change colors. This counteranion will actually react with the silver oxide and it will precipitate out. And what happens is the silver will coordinate with the iodine and form a solid that precipitates out of solution. And during this reaction, you generate hydroxide. And then this hydroxide can do the same reaction where it can go up, it can grab this proton, that proton can clamp down, and it can kick off the leaving group. So this can do the same sort of chemistry. So then the question is, well, why would we want to do this route over just adding sodium hydroxide as a second step? Well, let's try to determine why. This route is useful because it is less basic. It is more gentle. Even though we're generating hydroxide, the hydroxide that we're generating here is in a much lower concentration, and we're driving the formation of the hydroxide by precipitating out that silver iodide from solution. So it's another way to accomplish this Hofmann elimination. All right, so I know you might be thinking, well, this has nothing to do with the less substituted alkene. Why does it give the less substituted alkene in this case? Well, let's take a look at this in more detail. So we'll look at the regiochemistry. And we'll do a little bit of review here because I think it's important to kind of brush up on some of this. So let's take a look at this reaction. We've got a chiral amine in this case, and we're going to treat this with excess methyl iodide. And by doing that, we're going to alkylate our amine all the way to that quaternary ammonium salt. So now we've got 3 methyl groups hanging off of it. Again, we've got this counteranion, iodide. So if we want to, what we can do is treat this with silver 1 oxide, nice gentle reagent, and that is going to react with that iodide. We're going to make silver iodide that will precipitate out of solution. We'll also make some hydroxide in solution. And then we'll also have our starting materials. So we've got our alkylated quaternary ammonium salt, and now we've got a choice to make, right? Because the alpha position is the one with our leaving group, but this time we've got two beta positions, not equivalent to one another, right? So let's color code them. Over here, I'm going to do beta positions in red. So these beta protons are going to be very reactive. And we also have beta positions over here. In this case, I'm not going to bother with dashes and wedges because it doesn't really matter. All right, so we've got a choice. Which of these are we going to go after? And as you can imagine, it's called Hofmann Elimination. We're probably going to go after the blue ones. So let's determine why. So we know just from the name, it's likely going to go after that, but let's draw this a little bit differently. And in order to do this, what I want to do is imagine looking down this bond. Okay, so we'll do that Newman projection. And if we do this, the front carbon has all three hydrogens coming off of it, right? And then the back carbon, if we think about it, it'll have that nitrogen group off to the left. It'll have a hydrogen over here, and it'll have an ethyl group underneath, right? So let's take a look at this. This is the conformation that we know is likely to take place. Well, let's compare that. Let's compare it to this view. What happens if we look down this bond? Well, we would get a different orientation. In the front position, we'd have two hydrogen legs sticking down. We would have a methyl group sticking up. And then back here, we could look at the back carbon and we'd say, well, the back carbon now has the quaternary ammonium salt kind of off to the right. And we'd have a methyl group underneath. And we'd have a hydrogen over here. So let's take a look here. In order for the red box to occur, we have to have a beta proton that's anti-coplanar to our leaving group, right? And in order for the E2 reaction in the blue box to occur, we have to have the same situation. It needs to be anti, right? Okay, so let's determine, well, why would the blue ones go faster even though it's a smaller base? Well, in this case, it's primarily due to this steric clash. And if you remember, this is called a Gauss interaction, which means that this is less stable. And it also means that this is just less likely. So that means that even though we're dealing with a small base, it's just less likely that we're going to go after either one of those red protons, because regardless of which one we go after, we're going to have this destabilizing Gauss interaction taking place. This methyl group, meaning this one right here, would much rather be in that anticoplanar spot. But if we do that, then no E2 chemistry can occur, right? So because of this, this is the least stable conformation. The CH3 would prefer to occupy the anticoplanar position. All right, I'm not going to go through and draw all of the Newman projections, but if you want to at home, you can draw the other Newman projection and you can see that that will give you a more stable interaction. You'll still have an interaction with this methyl group down here, but that's a lot less sterically repulsive than running into that alkylated nitrogen group. All right, so we know that the blue pathway is far more likely, which means that we're going to get the Hofmann elimination product, hence the Hofmann reaction, and we'll kick off our amine. So if you just want to remember, hey, anytime you alkylate an amine and you do E2 chemistry with it, you get your Hofmann product, that's fine too. But as you can see, the Newman projections actually explain kind of what's going on here. In this case, this is already in the most stable conformation. All right, so that's where we're going to stop today. Next video, what we're going to do is we're going to look at a new reaction of amines where we look at preparation and reactivity of diazonium salts.